All right, other questions about stuff from before the exam before we go on?
So your L value always has to be n minus 1, correct?
No, that's the greatest number that it can be. But the
Okay.
L specifies what subshell it is,
Okay.
or sublevel.
Okay.
So S is 0, E is 1, D is 2, and F is 3.
Okay.
Anything else? Okay, let's take a look where we left off here. So we were doing some stuff with electron configurations. Let me pull up the pictures here too. And the point of doing that, which I don't know if we really talked about because we didn't quite get there, is that the electron configuration ultimately dictates chemistry. You can predict chemical or physical properties of materials and of elements based on their electron configurations, and more specifically their valence electrons. And if you go on in chemistry, if you go to organic chemistry, if you go on to inorganic chemistry and whatever else, they will continue to always be talking about how those electron configurations influence the actual, like, what's happening. People who design, for instance, solar panels, you need to figure out how to engineer chemicals that absorb certain wavelengths of light. And you do that by looking at the valence electrons and kind of figuring out what they do and how they transfer between atoms. So that's where all this comes from. And we're going to see a few examples of that now. The valence electrons can, and specifically where those electrons are, can give us some clues about what we call the periodic trends. So periodic trends are just like as you move across the periodic table, what happens, or as you move up or down the periodic table, what happens. And so the first one we're going to look at is atomic size, so the size of an atom. Anybody have any guesses as to what you think affects atomic size?
Number of protons in the nucleus.
So one thing is just going to be the number of protons in the nucleus. Why?
Because they have positive charge, so they'll attract electrons towards them.
Okay, sure, but so then the real result of that then is that they have more electrons, right? Because the electrons are the kind of outermost things. So that makes sense. The more you have, the bigger the thing goes. But as we'll see, that trend does not quite work all throughout the periodic table. So let's see what we actually have for periodic trends for atomic size. I'm going to put this in the notes because we're going to talk about it a bit. Probably doesn't need to be quite that big. Okay. So here's some trends on atomic size. As the atomic number increases, going from left to right, the y-axis gives you the atomic radius, so the size of the atom. So as you can see, if you kind of average this whole thing together, in general, what Chris said was right. As the atoms get bigger, generally, the atomic size kind of trends upwards. Everybody kind of see that? But if you zoom in a little bit, it's not that simple. So what do you think this like bouncing behavior is doing? What's going on there? The fact that it like kind of jumps up and then creeps down and then jumps up, creeps down. Yeah.
Does that do with the orbital that the electrons are in?
It does, yes. What types of atoms are big? Bigger than you would expect, let's say, for this trend? The alkali metals, right? That's where it seems to kind of like jump way back up again. And then, so as you can see, it kind of goes down from the alkali metal and then jumps back up when you get to the next one. What happens when you get to the next alkali metal, electron-wise? What does that mean when you get to the next alkali metal?
Gained electrons, right?
Yeah, so yes, you're gaining an electron, but we're gaining an electron through the middle parts there too. The big difference when we jump to the next alkali metal is we're jumping to the next n level. So if we think about where the valence electrons are, let's look at lithium versus sodium, for instance. So lithium is, again. Lithium is He, helium, then 2s1. So its valence electrons are 2s1. Sodium, valence electron is 3s1. Potassium, for S1. So what can you say about as you increase the n level, what happens to the atomic size? It increases. A couple ways we can say that. One is just like that. So as n level increases, so does the atomic size, the size of the atom. All right. But so then let's look at the other parts. Actually, before we do that, let's talk about why. So that's, remember the law of theory thing, the observations versus the explanations. So here's our what? Our observation. As n level increases, the atomic size increases also. What do you think is the why for that? Why does the atomic level, or does the atomic size increase when the n level increases? What's happening in the atom that's causing that to happen?
You're adding a further out orbital?
Yeah, exactly. You're adding a further out orbital. So each successive n level is farther from the nucleus. So if you're adding electrons farther from the nucleus and farther from the nucleus and farther from the nucleus, you're making the atom bigger and bigger and bigger. So the higher n levels should be bigger than the previous ones. So now let's look at the weirder part. As you go in a period, so as you go from lithium to neon, what happens to the atomic size? It decreases. And that maybe doesn't make sense because you're adding electrons, you're adding protons, you're adding electrons as you go across. Why is the size decreasing? Any ideas? Yeah, thank you.
If you have more electrons, doesn't it have a tighter pull towards the inside?
Yeah, exactly. So when you're adding electrons in the same period, you're adding them to the same n level. So basically the same spot in the atom. But because there's now more protons and more electrons, there's a stronger attraction. And so there's a contraction that happens by that stronger pull between the positive and negative charges. So even though we're adding more, because we're adding them to roughly the same place, the same shell, and then there's more attraction between the protons and the electrons, we are increasing that pull and making it a bit smaller. Let's see, let's word this a little bit differently. So the size decreases as you go across the periodic table. We can also explain this from that idea of effective nuclear charge. Remember we talked about shielding? So the inner core electrons shield the outer core electrons from that pole. So if you have, let's say, an alkali metal, you've got one lonely valence electron out here that is being shielded from nuclear charge by all the internal electrons, all the core electrons. And so that one electron is really not feeling that much pull because of all the shielding. As you go across the periodic table, since you're adding protons, each of those electrons in that outer shell are now experiencing a greater effective nuclear charge because they're still shielded by the same number of core electrons. As you go across, you've got the same number of core electrons. You're only adding valence electrons, which don't shield each other. So the bigger charge in the nucleus, coupled with the same core electron, the same shielding, is going to give you more pull and is going to lead to that atomic contraction. And this idea of effective nuclear charge and how that affects things is going to be the case, pretty much the explanation for everything else we talk about in the rest of this chapter. So thinking about how a valence electron may or may not be influenced by shielding is going to be the answer to a lot of these questions of why something happens. Okay, so that's atomic size. We see some weirdness going on in the transition metals, but an overall decrease throughout there. That happens with the lanthanides as well, which are not shown here. It stops just after cesium. But as you go through like period 6, you get an even bigger contraction through the lanthanides, again for the same reason. You're adding electrons, but you're adding protons, and so you're getting this kind of behavior going on. The reason it's not totally perfectly even, as you can see, there's some little blips. It's because, of course, there's always other sort of complicated things going on. There's electrons jumping back and forth between shells as they get closer in energy. There's other weirdness. In size, we're not going to focus too much on the weird exceptions. When we talk about ionization energy, we will a little bit. All right, so just keep thinking about that word, effective nuclear charge. And let's look a little bit at electronic properties. So first, actually, hold on. Before we do that, let's skip that for now. One thing that we did not talk about is the electron configurations of ions. You could probably guess how this would go, but there are a couple special things that we need to look at. So for instance, with some, it's very straightforward. If we look at a calcium atom, the electron configuration is argon and then 4s2. We know that the most common ion of calcium is what? 2+, yep. So what do you think the electron configuration of calcium 2+ is? Just argon, right, yeah. Right. Simple enough. And in fact, one way that we can predict ionic charges is from or from the idea that a noble gas configuration is particularly stable because everything is full, all the shells are full. So several chapters ago, we talked about, okay, the alkaline earth metals are always +2, the halogens are -1, oxygen is -2. There wasn't really a reason for it at the time, we just said that's what it was. But now we can think about it in terms of electron configurations and see that there is absolutely a reason for it, in that those ions are the noble gas configurations. So if we looked again at oxygen is 2s2, 2p4. And what's the common ion of oxygen? Minus, right? Oxide 2-. And its configuration, if we're adding 2 electrons to it, not helium. Oh, this is supposed to be helium.
Yeah.
Yeah. This is supposed to be neon. So, or another way we could write that is to actually show that it's got a full shell helium 2s2 2p6. That's the same thing. Means the same thing. So oxygen gains those 2 electrons so that it can achieve noble gas configuration, which is especially stable. And that works throughout the main group elements. The right side, what we call kind of the nonmetals, and even down into some of those metals. And then on the left side, the alkaline metals, the alkaline earth metals, the ones that we said had predictable charges. Now the ones in the middle, we know they don't have predictable charges, and in fact, they can have multiple different charges often. And so the way that they make ions is a little bit different from an electron configuration standpoint. If we look at vanadium, V, which is element 23, you can see that it is the third element in on the D block. So that tells us, and it's just past the S block, so that tells us that its configuration is argon 4s2 3d3. And pretty much all the transition metals, with a couple exceptions, make +2 ions. That's the most common ion of the transition metals. And the configuration for those +2 ions has lost the 2 s electrons. And that's in fact why those configurations are so common. Even though we say that we fill the s electrons first when we write the electron configuration, the s electrons are actually higher in energy. What really happens is, if you really want to talk about like what's happening, the d electrons are filled first. So vanadium would fill 5 electrons in the d's, but then 2 of them end up jumping up to the s for various fairly complicated reasons about things like spin orbit coupling, some other things that are going on. So the 2 of those electrons end up getting promoted up to the s. But those are still the highest energy electrons. The highest energy outermost electrons are the ones that are going to be removed when you make a positive ion. So even though we talk about the s coming in first, those are actually the highest energy ones, the highest n level. Those need to be removed first. So any transition metal is going to have a 2+ ion where it loses those 2 electrons, with the exception of silver, which does not make a 2+ ion. Higher, more positive ions of the transition metals are also possible in some cases. So for instance, there is an iron +3. So if iron is D6, there's an iron +2, but there's also an iron +3. In the iron +3, you would remove the 2 s electrons, the 2 4s electrons, and then you'd also remove one of the d electrons, because you have to remove 3 electrons to make a +3 ion. So we have 3d5. All right, so that's how you write electron configurations of ions. For other ones, like down in the F block, or some of the like lower metals like lead or something like that, same rules apply. Those are going to lose the outer, they're going to lose from the outer to the inner. So they're going to lose the, like lead, for instance, is going to lose its 6p first. Then it's going to start losing the 5d, and then the 4f, and so on. Or I'm sorry, the 6p, then the 6s, and then those other ones. All right. So one consequence of this is that these atoms and ions can have magnetic properties. They can interact with magnetic fields. And there are 2 words that describe how these things are going to interact with magnetic fields. One is called paramagnetic. And one is called diamagnetic. Both of these terms are different from what we think of as a magnet. So like a solid magnet, like an iron magnet that you put on your door, or a rare earth magnet that sticks to something. That's called ferromagnetism. That's a different effect. It has to do with effects of a whole solid. These are individual atoms or molecules can be paramagnetic or diamagnetic, and it's based on unpaired electrons. So a paramagnetic compound or element has unpaired electrons and is attracted to a magnetic field. And diamagnetic, as you'd expect, is the opposite. Has no unpaired electrons. And is repelled by a magnetic field. And we can figure out if it has paired electrons or not based on its electron configuration. So let's look up at some of these that we looked at. So would a calcium 2+ ion be paramagnetic or diamagnetic? It would be diamagnetic because it has no unpaired electrons. They're all paired up. What about an oxygen neutral atom, 2s2, 2p4? Would that have unpaired electrons? It would, because even though they're even numbers, we know that there's 3 p orbitals, and so the electrons are going to spread out to not be paired up if they can. So that's going to have 2 sets of paired electrons and then 2 unpaired electrons in the oxygen atom. What about in the iron 3+ ion? Paramagnetic or diamagnetic? Paramagnetic, same thing. All of its d electrons would be unpaired since there's 5 d orbitals. You see how that works? All right, so now let's talk about ionic sizes, ionic radii. And you can probably guess this, but let's see. Would you expect a positive ion to be smaller or larger than its neutral counterpart? Is a cation going to be smaller or larger than its neutral counterpart? Why larger? So I got some smallers and some largers. Anybody? So think about it for a minute. And what's your reasoning behind what you said?
Whichever has less electrons would be bigger, since there wouldn't be as much of an attraction, or does that not matter?
Okay, so if it has fewer electrons, it might have less attractive forces, and so it might get bigger because of that. Okay, we'll think about that. Stefan? That's what you were going to say too?
Could it also be smaller because there's still the same amount of protons, so there's more attraction for the electrons that are towards the nucleus?
Okay, that's a possibility too.
So I'm changing my answer.
You're going to change your answer?
Because they're becoming like the previous noble gas. So
Uh-huh.
the previous noble gas is down a valence level, so it's smaller.
Yeah, so it turns out there's a couple of different things going on that we have to think about. And I liked all of your reasonings. Cations are always smaller than their neutral counterparts. But for a couple different reasons, depending on the cation. So if we look at something like calcium, a neutral calcium has valence electrons in the 4s2. If it loses those 2 electrons and becomes a +2 ion, then it now has 20 protons still, but only 18 electrons. And its outermost electrons are now 1 shell lower. So you've dropped a shell and you have more protons than electrons, so you should have a pretty big contraction going on there. Other possibilities, like if you're not losing an entire shell's worth of electrons, you would still expect it to be smaller because of what you said, that you now have the same number of protons but fewer electrons. So even if you haven't dropped a whole shell, if you have fewer electrons for the same number of protons, each of those electrons has a higher effective nuclear charge. It's feeling more of a pull from the nucleus. And so that whole thing is going to get contracted and get smaller. So cations are always going to be smaller than their neutral counterparts, and they're actually generally quite a bit smaller. So for instance, just for some examples, so like we said, a calcium ion. A neutral calcium ion is 197 picometers in diameter, and a calcium 2+ ion is 99, so it's about half the size. Another thing that you'll see is in comparable size elements, what do you think is smaller? A +1 or a +2 or a +3 ion? So for instance, an isoelectronic atom. So potassium +1, calcium +2, scandium +3, let's say. Well, that one's not on here. So we'll say gallium +3. We'll just jump across from the transition metals. Those all have, except for gallium, they have roughly the same valence electrons, right? Same types of configurations. They all have argon configuration. Which one's smaller?
Yeah.
The +3. So the bigger the charge change, the more of that contraction you have, and so the smaller it's going to get. Potassium plus is 133 picometers, calcium 2+ is 99, and gallium 3+ is 62. So you see a big, big change there. So the cations are smaller than the neutral counterparts, and higher charges are smaller. And then also make sure that you know how to explain that in the way that we've just been talking about. So what exactly is causing this, and how can you describe that? How can you explain that? All right, so jumping to anions, what do you think happens? The opposite, very good. So anions are larger. What did I just do? Okay, so why are anions larger? So let's think about it for a minute. See if you can formulate a nice sentence or two explanation of what's going on with anions that would make them larger than their neutral counterparts. Think about it. You want to give it a try?
Just like a general statement, I guess. Could you say that for cations, the highest charge you'd be going the smallest, and then the highest charge for anions you'd be going the largest? Is that right?
That's right, but why? What's happening with the electrons that is actually causing that?
So based on the number of protons and electrons, because there's less of an electrical charge between the two, there won't be attracting all of them as much as
Yeah.
is the right word, but
Right, so that's exactly how you want to think about it. Is that what you're going to say too about the attractions? Yeah, think about those. What?
Does shielding also play a role in this because of the outermost shell?
Right, you're adding electrons to the outermost shell. You're not adding any electrons, or you're not adding any protons. So rather than a contraction, which is what happens when we add electrons and protons together, since you're only adding the electrons, there's now a smaller pull for each one, and so you end up expanding the size of the shell. Yep. So be careful just a little bit with your language with those. Make sure that you're saying the right thing. With anions, you're often not changing the N number. So when you're going from oxygen, neutral oxygen to oxygen -2, you're still in the N equals 2 shell. So it's not getting bigger because you're jumping up to the next shell, the way the cations often get smaller because you're jumping down a shell. But it is because of the change in the attraction from the nucleus, just as before. And as you'd expect, the trend continues from before, but it's just not quite as dramatic. So in this case, higher charged isoelectronic ions are larger. So if we look at like sulfur 2-, sulfide, and chloride, which is 1-, those both have argon configurations, but sulfide is bigger than chloride, 184 picometers to 181 picometers. Not a massive change, a small change. The change between the +1 and the +2 was a much larger change. Okay, any questions about size so far? Ionic change? Okay, let's look at some questions. If you haven't had a chance to look at these in the homework yet, well then we'll just try it now. All right, I'm gonna write 5 different atoms, and I want you to put them in order of decreasing atomic radius. And watch out with these. These like to show up as multiple choice questions, like on the final, and so, because it's an easy, there's just different orderings. But be careful, because if you read that wrong, like, okay, you put it in order of decreasing atomic radius, you could pretty easily flip that. And on a multiple choice, on a free answer question, I would say, oh, it's clear they just got this flip, but they got the order right, and you'd still get some points. But on a multiple choice question, if the flipped version is one of the choices, then you're just going to get that question wrong. So make sure you take a second to think about what that means. Decreasing atomic radius means that the largest one is on the left and the smallest one is on the right, and then you fill in the trend in between there. So give that a try. When you have a ranking, turn to a person close to you and see if their ranking is the same as yours, and discuss if you are different. How do you feel about your rankings?
Good.
Pretty good? Okay, what do you think is the largest one? Cesium, yep. So how did you know that would be the largest?
Furthest down and the most, I guess, just the left.
Yeah, furthest down and most to the left. So there are 2 atoms in period 6, cesium and lead. Cesium is way over on the left, the alkali metals, lead is over on the right. So by the time you go to from cesium to lead, you've done a lot of contracting, right? Done a lot of getting smaller. Okay, so it's often easiest to do these if you think about the extremes first. So what do you think is the smallest one? Probably sulfur. Yep. Okay, so how did you order the 2 in between there? So you've got selenium number 34, antimony 51, and lead 82.
Lead, antimony,
Yeah, so you'd go probably lead, antimony, and selenium. So you can see the pattern on the periodic table. You've got cesium way over here, so that's going to be the biggest one. Then these 3 are kind of in order going up and to the right. So lead, antimony, selenium, that's going to keep getting smaller, both because you're going down an N level, but also increasing the number of electrons. That's a trend. These questions have to be chosen a little bit carefully. Yeah, go ahead, Nikki.
Oh, I was just gonna ask if, I think there was an example in the homework where, like, let's say you had gallium and tin.
Mm-hmm.
Gallium's higher, but tin is further to the right, and I think the
Right.
answer was impossible to tell. Would we see something like that on the exam, or would it just not get asked?
It probably just wouldn't get asked without more data. But you can, right, so in this, like if you're comparing things in this direction, it's fairly straightforward like what we just did. But if you're comparing things in this direction, it's not, because the forces are competing. If we go back up to look at that graph, okay, so like for your example, what was it, gallium versus tin? Right, so gallium is like here, and tin is like here. So it's really hard to make that comparison because they kind of have different trends a little bit. So you really need to look up those numbers when it comes to things like that. This is not necessarily obvious just from looking at the periodic table. And you can see some examples where here, there could be some weird effects. So for instance, because this effect is so strong, something like sodium or magnesium is larger than these transition metals that are a much, much bigger shell because of all of that contraction. So comparing something over on the left to something down and on the right can be really difficult because they can be hard to balance. One good rule of thumb is just that the alkali metals are definitely the biggest. As you can see, they're on the very top, and there's nothing even, well, I guess until you get way over here into the 6th row, you don't really, well, 5th row at least, you don't really get stuff that's bigger than even lithium, but certainly not sodium or potassium. So the alkali metals are quite big. Good so far? Okay. Next trend is something called ionization energy. And I'm hoping that now that we've talked about this a little bit, we can kind of think about what we already know to make some predictions rather than just trying to like memorize some rules. So ionization energy has a specific meaning and a specific value. It is the energy required to remove an electron in the gas state. So you have a gas, which means you have totally free atoms that aren't interacted at all. How much energy does it take to put in that system to release that electron? We talked about that a little bit in the last chapter, where you can calculate that for something like a hydrogen atom based on its promoting the electron up through those levels. For other atoms, we can also talk about ionization energy, but it's harder to do it theoretically, but you can measure it. You can measure how much energy it takes to get rid of that electron. So before we put anything down here, what do you think about ionization energy? Which atoms, if you look at the periodic table, which types of atoms or families of atoms or areas of atoms would you think it's the most easy to remove an electron from? So I see a couple people kind of pointing to the left. Why?
Because it's easier to go down to the lower valence than it is. They want you to go to the full valence. So losing an electron is the easiest way to do it.
Yep, so that's part of it. Yep.
It'd be harder to do it more to the right because that's where you have the negative charges.
Yes, I think you're on the right track with that. Yes. Anybody else? Those sound good? Yeah, there's again kind of two things going on. So one thing is, when you lose electrons, sometimes you get to a very stable, specially stable configuration. So if we look at the alkali metals, if they lose one electron, then they become noble gases, and we know that's especially stable. So that's going to make it especially easy for those particular atoms to lose that electron. What else? When we talk about other atoms, and this is what I think you were getting at, if we talk about the other atoms that are not alkali metals, if they're just losing one electron, it's still true that the ones further to the left have an easier time of losing that electron. What's happening inside the atom that's making that happen? I'll give you a hint. It has to do with the same kind of reasons we've been talking about with all the other stuff.
It's the fulcrum's the number of protons versus number of electrons. So when there's more protons and more electrons, there's more of an electromagnetic pull. Or there's more of a pull versus when there's less of each, there's less pull, and there's also, they're affected by the shielding from the full valences. Otherwise.
Yes, so as you move to the atoms on the left, the outermost electrons, the valence electrons, are the most shielded from the nucleus because there's fewer valence electrons compared to core electrons. So you have less of that effective nuclear charge, and therefore those electrons are attracted less strongly, and they can be kicked out. As you move to the right, just like with the size, you have that greater pull, that lower shielding, that greater effective nuclear charge, and then those electrons can't leave as easily. So the same reasons, we're still looking at effective nuclear charge and how strongly the electrons are attracted to make these types of conclusions. So let's take a look again at a graph of the trends in the first ionization energy. There are successive ionization energies. So you can have first ionization energies, which is removing the first electron. Then you can have a second ionization energy, removing the second electron, then the third one, and so on. You can remove as many electrons as you want if you have enough energy. Whoops. Oh, stop. All right, that's good enough. Do you ever have this thing where you like computers, but then sometimes you don't like computers? All right, so here are the ionization energies, and you see kind of a similar but inverted behavior to what we saw with the charges. That as we go across the periodic table, the ionization energy is increasing. So a couple of things to notice about this. One, all first ionization energies are positive. So even though we talk about alkali metals being very, very reactive and wanting to lose their electron, it still requires you put energy in to kick that electron off. It's still an endothermic process. The reactivity comes in because all the stuff that's happening ends up releasing energy, and so it ends up being very energetically favorable to do that reaction. But to just remove an electron, even from a reactive element like the alkali metals, you still have to put in energy. And that energy is measured here in kilojoules per mole. So for instance, to remove an electron of sodium from neutral sodium, you have to put in 496 kilojoules for every mole of sodium atoms. That's the amount of energy you need per mole of atoms. So, as you can see, move to the right, the energy goes up. What about up and down the periodic table? Is it easier to remove electrons from atoms on the bottom or on the top?
Bottom's easier.
Bottom's a little easier. You see, like if you look at comparable atoms, lithium, sodium, potassium, rubidium, the trend is kind of going a little bit downward. Why do you think that is? Chris?
Further away from the nucleus because of the different layers of valence electrons.
Yeah, further away from the nucleus, you're going to have a lower electrostatic attraction, a lower Coulombic force between the nucleus and those valence electrons. So those electrons require less energy to be removed. Yep, that's right. Okay, so something else weird that's happening here. In the atomic size, we saw the same basic trends with just like some little random blips around. In this graph, do you notice any kind of weird patterns? So you drew it in the air. Do other people see it too?
There's three peaks.
Yeah, it kind of goes like, in every row, it like kind of goes up a couple, then jumps down, then goes up a couple, then jumps down, then goes up a couple. And it pretty much does that every time. It gets a little weirder down in the fifth row, but it's basically doing that every time. So that seems to me like that's not just a random thing. There's something causing that. There's something going on there.
So is it filling the up and down arrow boxes? So with the like with lithium, for example, it's only got one spin for that band for 1s or 2s1, then it goes to 2s2, and then it drops down to 1p, and it fills the three boxes
Mhm.
with one direction, then it drops back down once it starts adding electrons going the other direction.
Yeah, let's look specifically at what electrons are being removed. So this is ionization, which means we're removing an electron. So let's compare, we'll look at this one right here. So we've got sodium, magnesium, and then aluminum, silicon, phosphorus, sulfur, chlorine, and chlorine and argon. Okay, so the valence electrons for those, sodium, the valence electron is the 3s1. Then we've got 3s2, and then 3s2, 3p1, 3p2, 3p3, 3p4, and so on, up to 3s2, 3p6. So we look at that first blip. What we're basically saying is that the ionization energy of aluminum, which is right there, is lower than expected. So instead of continuing that trend upward, it jumps down. And we might say that the reason for that is because removing that 3p electron, which is a little bit higher in energy, leaves a full s shell. So you're removing an electron that's a little bit higher in energy, and it's maybe a little bit less energy than we expected to remove that then, to leave the whole shell. And then what's going on up here? So then we've got aluminum, silicon, phosphorus, and then sulfur is right there. Sulfur is also a little bit lower than expected. So what do you think's going on there?
3p4, so it's when you, like I said, it was when you add the other spin going down, so it's, you always fill them going in one direction than the other, so it's,
Right.
it likes being, I'm just like, I can't put it, I don't know.
Yeah, you're almost there. So, right, so the sulfur is 3p4. 3p4 is 2 unpaired electrons and 1 pair, right? if you remove one electron from 3p4, you make 3p3. So you're going from 2 unpaired and 2 paired to 3 unpaired. We know there's that electrons repel each other, so we're essentially pulling that paired electron out, and this electron can relax and go, oh, finally, that guy's gone. And so then it's going to be a little bit lower in energy than we would expect. So it's a little bit easier to remove that 4p electron, that p4 electron, the fourth p electron, than maybe is expected, because you have that extra pairing energy to contend with. Anybody ever feel relaxed when someone leaves? It's probably a particular person you're thinking of in your head. Maybe it's me. I don't know. Yeah, and so you can see the same pattern happening row after row after row, and that's how we can explain it, by thinking about which electrons are being ionized and what does that do energy-wise. Does it make it a more stable situation, a less stable situation, so on. Okay. So that's trends in ionization energies. And so one of the things that I'm going to ask you to do, and we'll practice it in a little bit, is one, to rank ionization energies, just like we did with sizes. So you pick out some elements. Can you put them in order of ionization energy? But then also, can you explain it with these ideas of nuclear attraction, of which types of electrons are being removed?
On a test, can we draw it?
Yeah, I mean, unless it's a multiple choice question, sure. Yeah. Yeah.
So those two little peaks, are they always happening when the S shell fills up and then when the P shell fills up?
Right.
Okay.
Yeah. Yeah, you see it there. So they're always kind of right in that same spot. There's a little bit of similar weirdness happening in d orbitals, so that's why you have these little weird shapes in the d orbitals going on. And then when you get to lower, and there's other kind of weird stuff going on. But yeah, we don't have to get into all that. Okay, another interesting thing that we can look at is successive ionization energies. So if we have like magnesium, for instance. The first ionization energy, where we call IE1, is 738 kilojoules per mole. So it takes 738 kilojoules to remove an electron from a mole of magnesium atoms. The second ionization energy is, all right, so now we have magnesium plus 1 because we removed one electron. Let's take another electron off of magnesium. Successive ionization energies always are higher. It always costs more energy to pull more electrons off of an atom. Even if it kind of puts them in a more stable state, it still costs more energy to do that. So the second ionization energy for magnesium is 1,450 kilojoules per mole. And then the third ionization energy, so we've removed 2 electrons from magnesium. Now we're going to remove a third electron from magnesium, is enormous. 7,730 kilojoules per mole. So between the first and second ionization energy, it's like roughly double. And then for the third ionization energy, it's like 5 times bigger. So why? Why is the third ionization energy for magnesium so much bigger than the other two? Amy?
I mean, because every time you remove an electron, there's going to be a stronger pull towards the nucleus, so it's going to be harder to then pull it away.
That's true, but what's special about the third one compared to the other two? Like, so instead of getting like a nice kind of linear increase, or even a slightly not linear increase, we're getting like 1, 2, and then 3. And it's like a huge difference. Julia, I think you're up
Would
first.
it have anything to do with like when you're in the acid, there's only 2 in there, so then you're going to a new shell?
Yes. Stefan, you want to add to that?
Isn't it at its like most stable form? Because technically it has the
Yes.
same configuration as neon would.
Also correct. Anything else? So what types of electrons are you removing? How would we categorize those first two electrons?
Oh, wait, it wouldn't have any valence.
Yeah, the first two electrons are valence electrons. So we remove the 2 from the valence, and everything's good. And then if we want to remove a third electron, we're actually removing it from the core. And the core now has extremely high effective nuclear charge, is attracted very, very strongly. We essentially never mess with the core electrons. They don't really do chemistry, and it's because of things like this. They're attracted so strongly that it costs a lot more energy to remove them. So those first two ionization energies are removing valence electrons, and this one is now removing a core electron. So one type of problem that that you'll see in the homework is it'll give you a set of ionization energies, 1, 2, 3, 4, 5, whatever, and ask you which element are we talking about. So let's try that. Consider these ionization energies. And these are all in kilojoules per mole. One, 578. 2, 1820. 3, 2750. 4, 11,600. And so then the question is, which third period element are we talking about? Which third period element has these successive ionization energies? What do you think? Aluminum? Or aluminium? Canadian or British? Yeah, how do you know that?
Because the largest jump is between 3 and 4.
Yes. Does everybody see that? So you find where that big jump is, and that tells you the big jump is right here. So that tells you that these are all valence electrons, and this is a core electron. So we're looking for the third period element that has 3 valence electrons, which is aluminum. There's a table in the book where you can see that. We won't put it in the notes, but you can see for all of the second period elements there, sodium through argon, no, third period elements, sodium through argon, you can see the successive ionization energies, and you can see that kind of cutoff where it jumps up to a super, super high value when it starts taking those core electrons. What?
This is something I'll need to memorize.
No. But, whoops. This is something you should be able to figure out, like what we just did. So if you see that big jump, then yeah.
Will we always be given a period if we're asking a question like that?
Yeah, you'd have to be, because it would be because there's no way of knowing otherwise, right? Yeah. Right. Right. Okay. So there are 2 more trends we're going to look at that are, again, related to all these other ones and have similar reasons behind them. And so you can use similar reasoning to understand them. Electron affinity is the next one we're going to look at. Be a little careful with this one. It often gets confused with electronegativity, which is something we'll talk about in the next chapter, and it's a little bit different. Electron affinity is the energy change associated with gaining an electron, again in the gaseous state. So how much energy is either gained or released by an electron adding to an atom? That's a very specific definition. So that's why it's a little different from what we're going to talk about later, electronegativity, which has more to do with the behavior in a compound. This is specifically talking about the process by which an atom gains an electron, so it becomes an anion. Now this value can be either positive or negative, but we're usually only concerned with the negative values. Negative values means that it has given off energy by gaining an electron, and positive values is essentially saying this atom has no electron affinity. It doesn't want an electron. It doesn't gain anything by getting that electron, or it just won't do it. So so here's a chart of some electron affinities. We don't even bother with most of the periodic table because metals, specifically transition metals, tend not to really have any electron affinities. They're mostly positive. So you can see some of the trends going on there that, as you would expect, most of the atoms that we know form anions readily, like fluorine, chlorine, oxygen, have pretty large magnitude electron affinities. You can see that in some cases. You can also see some weird kind of exceptions going on here. Like nitrogen. What do you think might be going on there? Why does nitrogen seemingly randomly have a positive electron affinity? So what that's telling us is that there's some problem energy-wise. It's not really energetically favorable for nitrogen to gain an electron. Why do you think that might be? Yeah, so what happens if you try to put that fourth one in, what does it have to do? It has to pair up with another electron. So it already has 3, 1 in each p orbital. If you put in a fourth one, it's got to pair up. So that's telling us that the energy gained by having that extra electron is offset by the energy cost to pairing electrons. And that's why it's an overall negative value. You can see the same thing with phosphorus and arsenic. It's not 0, but there's still this kind of dip all of a sudden because it now has to pair up electrons. In those lower ones, the net energy is still, you're still releasing energy on net. There's still a gain or a release of energy associated with that change, but it's maybe less than expected because of that pairing energy. So you can see that same kind of thing. Basically the same spot that we saw the blip in the ionization energy is just the opposite process. The other thing to watch out for with electron affinities is the language a little bit. So because these are reported with negatives, when we talk about a larger electron affinity, we're really talking about a more negative electron affinity, a larger magnitude of the electron affinity.
Why is 3p so much more, why is 3p the most likely to take on an electron versus the others?
What do you mean?
So like, for example, chlorine has a negative 349, but fluorine and bromine are both lower than it. So it's not like it's directional one way or another.
Oh, so you're saying like,
the third
so as it
period,
goes down,
the third period has the most.
I have an idea, but I'm not sure.
Otherwise, the other one, I didn't know if there's a reason.
There is. I'm sure there is a reason. I don't know what it is for sure. My guess is it has to do with the specific energies of the p orbitals in that shell and the degree to which it can that those energies are stabilized by having extra electrons in them. That those orbitals are. But we'll look it up and we'll find out for sure because that's an interesting question. Okay, and the last one is probably the easiest trend of all. And that is what we call metallic character. Metallic character is a little bit squishier of a definition than the other ones. It doesn't refer to a specific process or characteristic, but it refers to kind of an aggregate, how well does this thing perform as a metal? And when we say perform as a metal, what do we mean? What are some properties of metals, do you know? What are some things that metals do that other things don't do? Conduct electricity is one. Metals are highly conductive. Non-metals usually not. What else? Any other ideas of what metals do?
They're soluble when paired with. They tend to be soluble when they're paired with like.
Well, we're not talking about the ions. We're talking about the actual metals, like the elements. Have you all seen metals before? So what are they like? If you saw a thing, would you know if it was a metal or not? They're shiny. Yep, they're shiny. They have that luster. They reflect light in that particular way.
Dense or heavy?
That's not necessarily. That's mostly because of how dense and heavy they are. But things like, heavy, like things like tellurium or something that's not really a metal is still going to be very dense because of it's a big element.
So is there a specific trend then for electron affinity?
For electron affinity?
Yeah.
Yeah, mostly it goes. It's going to increase larger negative values as you go to the right toward the ions, with the exception that we talked about right in the middle there. Yeah. All right. So with metals we talked about conducting electricity, shiny. Another one is that we say that they're malleable, which means has anybody ever taken a hammer to a car? Someone you didn't like, you just sort of like. Is there a difference between if you just smack the side of a car versus the window?
Yeah.
Oh, okay. Anybody have experience with that?
Well,
No?
And there will
No.
shatter,
Tires.
metal will bend or give.
Yeah, the metal bends or gives. So that's its malleability. What's really happening there has to do with the electrons. In a metal, the electrons are not localized on the individual atom. They're delocalized. They're sort of just everywhere around the atoms. So you can reorganize the atoms, and the electrons kind of fill in the spaces. So when you hit a metal, you're reorganizing the atoms, and the electrons kind of just fill in, and everything's good. A non-metal or a material like glass, the electrons are localized on their atoms. So when you smash it and push the atoms apart physically, the electrons go with them and you make a break. So that's how you get something that's brittle. And of course there's various ways you can measure that, and there's kind of ranges of that. But the basic idea is that metallic character, so the degree to which something acts like a metal, increases, is more metallic, increases as you go down and to the left. And the reason that one's easiest, I think, to remember is where are the metals on the periodic table? They're on the left, right? And where are the nonmetals? They're on the right. And even the little divider thing is kind of like a line, and if you went up and crossed that line, you can kind of remember that trend. So down and to the left are the most metallic acting metals. Up and to the right are the least metallic acting nonmetals. All right. Feel good about all that? You can do some trends. So with Chapter 8 homework, if you haven't had a chance to do it yet or you haven't had a chance to finish it, or even if you have finished it, You might want to go back and just take a look and make sure that you can answer these questions about the different trends, but also justify them. Remember that when you're doing your homework, it's very easy to just look stuff up. You can look up the numbers and kind of just fill stuff in that makes sense. But when you're at an exam, you may not have those resources. So if you can explain to yourself the actual concepts behind what's going on, then you can usually figure out the answer to these trends questions if you're thinking about things like the effective nuclear charge and all of that, even when you don't have access to the actual table. So if you've done it, if you looked stuff up, that's fine, but maybe go back and look through some of the questions and see if you can do it without looking up the numbers. Sound good? All right, let's stop there and take a break because that's the end of chapter 8, and then we'll get into some chapter 9 stuff.